All right, good afternoon, everyone. Welcome to this presentation. I'm Hugo Nestor Villegas Pico. Pulpentera Assistant Professor at Iowa State University. A little bit of my background. I think it was discussed. The focus of my research is on reliability aspects of power systems to faults and their resiliency to blackouts. My research at the intersection of four domains: power electronics, power systems, control systems, electric machinery. My research is just a dot within that intersection. My research uses a lot of physics, mathematics, and computer science. I have conducted this kind of research at the National Renewable Energy Laboratory at Purdue, Iowa State University, and I have industry background. I was a supervisor of thermal power plants, which were Blackstart capable. So I was doing that work for a little bit more than 2 years. This presentation is based upon work funded by the U.S. Department of Energy, Office of Basic Energy Science, under award number SC00214110, and also funding also comes from the National Science Foundation, under grant number 2013739. I sincerely thank for the support from these federal institutions to conduct my research. So the related publications that I'm using to build up this presentation are shown here. Actually, we have conducted in my group contributions to the Blackstart capability and survivability of wind turbines with fully rated converters, also for Type 3 wind turbines, as well as for photovoltaic solar power plants. So I'm going to be merging a little bit of pieces within these papers in this presentation. So I'm telling this because you can have a reference where to refer to in case you have questions. Right. The main motivation for conducting the research on grid forming technology has been because of the relatively high penetration of wind energy resources in the state of Iowa. At present, we have more than 12 gigawatts of installed wind capacity, which should be contrast against the installed wind capacity that we used to have in year 2012, which was only 5. So we have grown a lot since then. Now, what does 12 gigawatts, well, a little bit more than 12 gigawatts mean in the state of Iowa? It means that wind turbines produce more than the 60% of the electricity that is consumed by the state of Iowa. Of course, we have Texas, which has the wind energy, when installed wind energy resources that account for 36 gigawatts of wind power. But that signifies for the state of Texas only a little bit more than the 20% of the electricity that is consumed in the state. So evidently, Iowa is becoming wind dominant and is growing at a very fast pace. And here in Iowa, we have been also hit by several challenges. One of those is, for example, the derecho event that happened in August 10 of 2020. So during the derecho event, that derecho event caused a lot of blackouts in the state. In fact, more than 600,000 customers lost power during that event, and of course we have to face a blackout. And blackouts have been also observed in other systems, for example, the South Australia system and the United Kingdom, which also have significant amount of wind energy resources. So where is Iowa? I'm trying to show here with my cursor. There is Iowa, and this is what I'm showing in this figure is the path of that directed storm that is called derecho. It comes actually from Spanish, derecho, straight. So it covers a straight line. Of course, the flow of the derecho covers a straight line. So and here is the different points in time at which that storm was passing for different areas. So I think here in Ames, we were hit almost at noon. I remember that day. It was very sad and tragic. So then because of this problem, because of these events, so what is the problem that we are trying to solve here? So the problem is that present wind turbines don't participate in restoration processes. So if we start thinking, if we are having the relatively high penetration of wind resources here in the state of Iowa, now we have to think in the future when we reach, for example, 100% penetration of wind renewable energy, wind resources. So how are we going to restore the system? For example, if we are hit again by a derecho. So one of the main reasons is that present control strategies, or why we cannot do this restoration with wind turbines, is because wind turbines, for example, use PLLs in their control systems, And then in turn, they need a synchronous machine to provide the reference voltage at the terminals of the wind turbine to restore. Then comes the question is, how do we restore a wind dominant power system? Of course, we need some kind of special set of controls. So here at Iowa State, of course, the objective is to restore a relatively large system. But here we first started with a relatively small system to understand what are the complexities of restoration processes. Of course, we already have been able to tackle the system that is on my left, on the left of the presentation. Now we are already tackling relatively large systems. But okay, so how do we do that? Okay, in order to achieve that, we have to make several contributions to the green forming technology. First, we introduce, a procedure to Blackstart and restore systems. So in the Blackstart and restoration, the goal is to re-energize, for example, transmission lines, to energize motor loads, which can be of two types, for example, three-phase motor loads, or it could be single-phase motor loads, could be, for example, in air conditioners, and three-phase motor loads could be, for example, in the auxiliary systems of I don't know, industry. It could be for pumping water. And also during the restoration process, it's typically the case that wind turbines have to withstand, for example, unbalanced load because there is no perfect balancing in the distribution systems. And nowadays, we are also challenged to energize power electronic loads, for example, electric vehicles. And those electric vehicles could be using relatively fast chargers, or it could be using other type of chargers, for example, type 1 and type 2, which usually withdraw relatively low power from the system. So what we develop in order to tackle this challenge, we developed two axis anti-wind PI regulators here. So the whole idea is was to invent a PI regulator that can bound control signals and the integrators of PI regulators, proportional integral regulators within a circle. So why was that necessary? Because we wanted to provide reliability to restoration impacts. So for example, the converters don't reach overrated currents. Also to provide reliability to symmetrical and asymmetrical fault events. For example, here I'm depicting a symmetrical fault event, a line-to-line fault event. For example, during the panhandle disturbance, line-to-line faults lead to the disconnection of more than 1 gigawatt of wind power. And the other challenge here, I mean, the good thing about these two axis anti-wind PI regulators, they can accept dispatch and frequency commands. And during the process, or during this work, it was also necessary to develop an anti-stalling and overspeed protection for the wind turbine. So we have one part is on the controlling about controlling the converter that is interfacing the grid, and another part is about controlling the wind turbine that actually is the primary energy resource. So there could be cases during the restoration process that wind speed reduces suddenly, and then at the instances, for example, the wind turbine can stall. Why? Because the converter that is interfacing the grid could be transferring more power than the turbine can provide. In that instances, then the wind turbine might start stalling. And then it was necessary to invent a new anti-stalling protection for reliable grid-forming operation. And actually, I call this survivability because we are trying to survive these long wind speed events during the restoration process. The whole goal is not to de-energize the grid during the restoration. And why I'm not using here batteries, because without batteries, the problem is tough. And we wanted to solve the tough problem there first, and then we can go to the easier one, that is when using batteries. And of course, to do this, we have also to come up with an upstream wind speed estimator. Some of the features that this controller have is that it has 4 volts per hertz control or protection. So the survivability is achieved by dropping voltage at the terminals of the wind turbines. During this, when survivability mode takes place, so it's necessary to have a tight control on the volts per hertz, because otherwise we can endanger the electromechanical energy conversion systems that are connected to the grid. Another aspect of this work that was very challenging was to devise a frequency controller for the wind power plant. So when we are restoring a system using gas turbines, we don't need this frequency controller, because the gas turbine usually is working in an isochronous mode, in which frequency is almost maintained fixed. But when we are using several, for example, relatively small capacity wind power plants, we want to have some we want to have some droop, some speed droop, in order for the wind turbines to work in parallel. But because of that droop low, then the frequency deviates from rated. So then we need to have a controller that can steer frequency of the wind power plant to rated. Of course, we didn't have this problem when we were using, for example, gas turbines. And another of the challenges is to use electromagnetic transit simulations to reproduce or to predict how these processes are going to take place in our future power systems, which was very, very nice. So at the end, why do we have to do this? I mean, who cares about doing this? So one of the first these contributions are needed is because we want to address the third grand challenge of the science of wind energy. We're required to have control systems for the wind turbines so that they can match the load and regulate voltages of the terminals of the different buses in the system, and as well as the terminals of the wind turbine. The other significance of this work is to engineer wind dominant grids that are reliable to faults and resilient to blackouts, and to restore, for example, the electric power that serves our communities, for example, the US taxpayers who are funding this research, and also to satisfy the North American Electric Reliability Corporation standards, for example, EOP 005-3 and EOP 006-3, which foresees the facilities, the personnel are prepared, for example, for restoration tasks. PRC 024-3, which is about providing the capability of wind turbines, for example, to remain connected as long as the voltage of the terminals and probably the frequency of the terminals remain within a particular prescribed bounds. The other why this work is also significant is because we want to support the worldwide initiatives for the reliable integration of wind resources, because if the Blackstart capability is not solved, then the penetration of wind turbines into the systems could be limited by this Blackstart problem. And recently, I think that what's very significant is that this work is also useful to address the specifications for grid-forming inverter-based resources that was placed by the UNIFI consortium in December of 2022. Okay, so what we have done here at Iowa State, okay, we have designed 4 control blocks to steer, for example, the Type 4 wind turbine that we are showing here in this picture. So this wind turbine has the grid side converter, the machine side converter. It has a step-up transformer that interconnects to the distribution system, and also has a pitch angle control of the wind turbine. And of course, here it has a permanent magnet synchronous generator. So we have one of the controllers is used to steer the grid side converter. So the mission of the grid side converter is to transfer power from the DC link into the AC side. Here by using the grid forming strategy, which is about regulating voltages at the terminals of the grid side converter, for example, here at these capacitors. And how do we achieve that is by regulating currents that are flowing through these inductors that are connected to the grid side converter. And of course, the angle of the reference trying to do all this job uses the classical droop control law. So we also have the machine side converter. The mission of this machine side converter is to regulate the DC link voltage, which in fact what it does is transfer power from the permanent magnet synchronous machine into the DC link voltage. The typical reference trains we use is the synchronous reference frame. We also have the turbine speed controller, which mission is to control the speed of the wind turbine. So the speed is achieved by controlling the pitch angle of the wind turbine blades. And as I was mentioning before, we also have a power plant frequency controller, which sends dispatch commands into the grid side converter controllers, for example. So here one feature is that the turbine speed controller is connected to the grid side controller. If you see here PE upper bar, PE upper bar. So we needed that interconnection. So if we put this in, if we recall about synchronous machine, the synchronous machine, for example, is connected through a shaft to the prime mover. So whenever there is problem on the synchronous machine, for example, the synchronous machine is overloaded, so that overloading is transmitted through the shaft to the prime mover. So here we only have the interconnection of the DC link, but the DC link cannot, for example, inform that the grid side converter is transferring more power than the wind turbine can provide. In that case, it's necessary, for example, to have control, to have communication between the wind turbine's speed and tell, for example, the grid side converter, hey, I'm stalling, do something, reduce the amount of power. So that is the communication that is happening here between the turbine speed controller and the grid side converter. So then we have here a sort of a virtual shop in order to interconnect the grid side converter and the permanent magnet synchronous machine. And the turbine actually. So in this presentation, I'm focusing on the grid side converter because it's relatively simpler, I think, to explain. So the ingredients that I'm using here are the QD voltage control by employing current by regulating currents, which was first proposed by Washington in his paper, A Voltage Control Strategy for Current Regulated PWM Inverters. But this strategy is already a grid-forming controller that was already developed in 1996. And of course, I'm employing also the Drude control law that was provided by Chandokar already in 1993. One characteristic of the paper, A Voltage Control Strategy for Current Regulated PWM Inverter, is that they use the synchronous reference frame. In fact, the speed of the reference frame is maintained fixed. So now we can now adapt this for system level by using the Drude control. And what we start here, the controller, is about transforming variables, right? For example, from ABC into a QD system via theta c. For example, theta c is the integral of the speed from the Drude control law. So here I'm using specialty transformations. For example, I'm transforming line-to-line voltages, for example, VABF and BCF into QD directly. The same current IA and IV, of course, the filter at the terminals of the inverter into QD, and the same for the current that is observed at the grid side or the low voltage side of the transformer. So this current is actually very important, the IAG, IBG, and ICG, or is a transformed version QDG, because this current is used for feed-forward control. So the whole idea is that, for example, this during an impact, for example, during a high current impact, this current IAG, IBG, and ICG are going to change drastically. So then the GSC can be programmed to compensate quickly for those currents in order to regulate voltage. Of course, within the limits of the switches that make up the grid side converter. So how we extended, right? Because these things are already standard. So what we did, we were tackling the full write-through capability problem. So in order to do that, what we did is we equip the present developments with a 2-axis anti-wind PI regulators. So the whole idea was to rewrite those PI regulators so that they can bound the control effort as well as the integration states within a circle. Why is necessary? Because the circle, or for example, in the abstract QD coordinate system, the radius of the circle models the voltage or current, the instantaneous voltage and currents of the waveforms in ABC variables. So it was necessary to do this control. So especially in this voltage regulator, current regulator setup, it was necessary to do this because, for example, the voltage regulator outputs current commands and the current regulator outputs voltage commands. So the voltage regulator current commands output are limited, for example, by the rating of the converter, whereas the voltage commands output out of the current regulator is limited by the amount of DC line voltage that is present at that particular point in time. So if this violates, if there is some violation in those variables, then there could be, for example, there could be controllability problems. Could be overcurrent problems, or in the case of the DC line voltage, it could be controllability problems. And here we are using also a feed-forward terms. The feed-forward terms I was mentioning before, we have here a component IQDG that compensates for the currents that are flowing into the low voltage side of the transformer. And also we have here the capacitor speed currents. That is because of the capacitor that we have at the terminals of the grid side converter. So then we can compensate for those currents in a relatively fast fashion. Okay, so why do we need to do this? So why don't we use, for example, the classical square banding approach? So in the classical square bounding approach, the problem is, for example, that the control effort is limited by a square, and of course the square over approximates the circle, and then that leads, for example, that some current commands, for example, takes values up to a square root of 2 times the rated of the value, which could be problematic. And however, this typical control strategy is relatively simple, right? We can use the typical anti-wind ups, right? We use the anti-wind ups for the integrators, and then we use we limit the control effort. For example, here IQD star, and then we have the actual control input into a QD process. For example, IQD star. This is asterisk. Let's call this asterisk. Okay, but the problem is that, as I mentioned, is that this is bounding in square and in lieu of a circle, which is amenable, for controlling QD axis systems. And so here, what I'm showing here is that how I'm modifying slightly actually this control in order to bound all the control signals and also the integrators within a circle. But yeah, I think it looks here like a magic, right? So we need to go and demonstrate what do we have here. But first, going into the demonstration, I would like to point out that this C is a function that actually bounds any point that is leaving, for example, the circle, so that finds a new point that is within the intersection of that point and the center, and also the boundary of the circle, and then they find a new point. And then that's actually what it's doing. This relatively function is bounding, right? Those points that are leaving the circle. Okay, so how do we achieve this two-axis anti-wind up PI regulator that bounds signals within circles? So we start from the classical two-axis PI regulators. Here we are controlling two variables, for example, the QD, and we have the proportional component that is so this proportional to the error, right? The control error, IQ star minus IQD, that is the process variable, plus theta QD, for example, that is the integrator, and plus the feed-forward control loops. And then, of course, in 3, we have the integrator. So how do we, in order to do the derivation of this, we first need to recognize the obvious. For example, from 2, we can recognize that KP times WQD star minus WQD equals IQD star minus theta QD minus IQD star. Okay, now in 3, we can recognize that is KP times omega, W star minus omega, or WQD is equals to the right-hand side of 4. And then we can substitute this right-hand side of 4 into 3, into this part of 3. And now we can get 6, actually find 6. And 6, and you can see now that the integrator has been written as if it were a first order system, which is steered by IQD asterisk minus IQD dagger. So these are the inputs that are driving the theta QD. Great. And this is what is called in control system literature the series implementation of a PI regulator. Okay, now the next step is to bound, for example, the control effort. Now, for example, we can bound IQD star using the bounding signal, the bounding function C. That what it does is bounds the control effort IQD asterisk into a circle or radius UMX, and that circle is entered in the region of coordinates QD. The next step, now we have this. Now the next step is to bound the inputs to the integrator, or the inputs that are driving the integrator. In this case, UQD star minus IQD dagger. So how we do that? We bound this with a circle also, IQD star minus IQD dagger. So this is important, actually, this, because IQD dagger, we don't know how large it could be, for example, during a transient. So then we can ensure that signal that is driving the PI regulators is bounded within the circle. So then we can do theta QD star. Of course, and then with that demonstration, then we have the two-axis anti-wind down PI regulator that can bound the control effort and the integrator within a circular radius UMX. while maintaining control directionality. The one thing that here is that when we are doing this bounding is we maintain the control directionality, which is very important in the control of multivariable systems. And I think here I'm just showing the set of equations that represents this block diagram that I'm having here in the picture that I'm showing here with the mouse. Right. Okay, so with that, so what we did is that from this general way of writing these PI regulators, we apply, okay, to to reconstruct the voltage regulator and the current regulator using this two-axis anti-wind down implementation, and of course with feed-forward currents. And it turns out that this control is relatively simple and is also elegant, which is, and most importantly is useful. With this controller, of course, there are some mathematical proofs. I'm not doing that, so you can refer to my papers. So it can bound the currents quite well. It can also withstand asymmetrical faults. You can withstand unloaded and unbalanced loading conditions, and so on. All the typical disturbances that wind turbines would be facing during the restoration. So in order to test or to evaluate this system, we constructed a waveform level simulation in Plex. We have also implemented in PSCAD this type of simulations. Actually, in PSCAD, we have been running large systems. But I always like to discuss about this system because it's relatively complex already to understand this system. There are a lot of signals that need to be tracked here. A lot of signals. At the first eye, it seems simple, but it's very complicated. All right, so the first challenge that we have to face is to start up motors. So we energize the motor, for example, at time t equals 7.5 seconds. So, and the motors, for example, start accelerating. So the motors were loaded with a there are two motors. Each motor is loaded with a 500 kilowatt pump. Okay, so and then the energization was successful. I mean, we had enough currents from the turbines to energize these motors. In total, it was 1 megawatt. So how much the wind turbines we have here? We have 6 megawatts wind turbines. Okay, so what was interesting when we're energizing the motors is that the motors, for example, at time t equals 10 seconds, had an overshoot of power that is withdrawn from the wind turbines. And at the same time, when this overshoot occurs, then the amount of reactive power that the motors are withdrawing from the wind turbines, you know, for the starting up process, reduces drastically. In that challenge, actually, the speed droop controller and the voltage controller. And I have to confess that at the beginning, when I was taking this project, I failed. I failed several times. Actually, I was testing, for example, some prototypes of grid forming controllers, and I was testing only one turbine. Then I was doing the restoration, everything with one turbine, and it worked fine. And then I added a second turbine, and then it failed. And especially it failed when I was starting up motors. So then it comes to me the conclusion that we have to be careful when we are designing these grid forming controllers. We need to make sure that, for example, several units in parallel are going to be able to remain in synchronism. Because what happened is when the motors were reaching this point, so then voltage and speed regulation was challenged, and then the turbines went out of sync. So it was challenging. I mean, I mean, when I was doing this, it was. I mean, I was sad at that because I thought I already got a prototype that was working, and then I tested with another turbine in parallel, and it didn't work. So and that's why you see here 3 turbines. So because I wanted to make sure that the turbines don't lose synchronism when they are, you know, taking over synchronization processes. I mean, taking over restoration processes, and that the synchronization is you know, is shown or is guaranteed during these processes. When restoring unbalanced loads, I didn't have any problem. I didn't observe any major problem. For example, here PC, it represents the amount of power that is withdrawn by the unbalanced load. You see here, this is black line is because there are 120 hertz oscillation because of the unbalanced nature of the load. There is nothing we can do. That happens also in synchronous machinery. So if the imbalance are low, then they're going to produce some 120 hertz oscillation. And the good thing is that it didn't stimulate any strange dynamics in the wind turbine. Here the time equals 17.5. We energize electronic load, this PE. So there was not a major problem. This electronic load is a 500 load. I forgot to mention about the constant impedance load that is unbalanced. It was withdrawing more than 2 megawatts from the grid. And at time t equals 20 seconds, we apply a fall. So when we apply the fall, what we observe is that there is a motor deceleration. It's because the motors lose the ability to generate electromagnetic torque to maintain the speed at rated. And also the mechanical power of, well, when actually the electrical power that the motors were withdrawing is reduced drastically, almost to zero. And of course, still have the oscillation because of the imbalanced natures of the fall. And the power by the unbalanced load is reduced almost to zero. And the power from the electronic load almost to zero. Of course, here I'm using only a resistor. Here there could be more complex processes, for example, the fast charging processes of an electric vehicle. But what is important is to observe the waveforms, right, when we are studying the falls. So, so here I'm showing the pre-disturbance waveforms, and during the disturbance waveforms and after the disturbance. So during the pre-disturbance part, here I'm showing the currents of the 3 wind turbines. So if you can see here, the currents are unbalanced previous to the fall. And that has to happen because I'm applying an unbalanced load. And you can see here the switchings. Also, the converters are switching at 3 kilohertz. During the fall, there is a slight spike, for example, in the current IF2, which is the current the inductor that is at the terminals of the grid side converter. So that current can go up to 3.6 kiloamperes. The IMX, the maximum, the limit that I'm setting up in the 2-axis anti-wind-up regulator is 3 kiloamperes. Of course, that the 3 kiloamperes is to bound the control set point, but it doesn't bound. There is no guarantee to bound, right, the actual control variable. So it spikes to 3.63 and then returns to 3 and remains bounded within 3 kiloamperes. And I applied this fall. I always maintain this fall active for more than half a second. At the point of the fall, the current, for example, at the line-to-line fall, at this point, the current just spiked to 0.82 kiloamperes. But of course, here we are observing at the 13.2 kilovolt side. The voltage of the terminals of the inverter or the voltage of the capacitor sag during the fall. And it's because what it happens with inverter is because there is it detects some high current, so it bounds the high current, and then the voltage drops immediately. So that's a consequence actually of controlling voltages by regulating currents, and that is expected here. I mean, it's Ohm's law, right? If you have a limited current, right, and you have constant impedance, and then voltage has to change in order to satisfy the Ohm's law. All right. So one important part also was to ascertain, that the turbines didn't lose synchronism during the fall. For example, here it can be ascertained, but by studying the relative speed of the droop control laws with respect to a reference one. So the reference one, for example, here I'm taking the weighted average of the 3 speeds that is provided by the droop control. So which is going to be omega-1 plus omega-2 plus omega-3, and here I think there is a typo. I apologize about this. So this is the weighted speed. So then we can take or we can study what is the difference of the speed of one of the droop controls of the turbine with respect to the average, and then we can study whether or not that is deviating from zero. So yeah, during the fall there was a little bit oscillation in the relative speed, and then the relative speed converts to zero. So here you see there are offsets. So because I wanted to show all these 3 in the same, all the 3 plots in the same axis. So I'm just subtracting -3, -6. During the fall, Also, the frequency rise a little bit, which is expected because of the amount of electric load that is lost, right, because of the fall. And of course, here, because the frequency rises, here we have the command from the frequency controller of the wind power plant, which tries to drop because the frequency is going high. So it tries to drop the power command of each of the wind turbines. And then once the fall is clear, then the fall is clear. Let's say that C7 opened by some miracle. And then now the system recovering again to a stationary steady state. So, and then you can see here voltage also recovering. There is a slight over voltage here during the recovery to 1.17, which is, I think, minor. Current grows a little bit higher than the currents that were previous to the fall, is because of the motors are recovering speed. So then they are withdrawing relatively high reactive currents for the speed recovery. We have extended this type of work also to do the Blackstart restoration of wind dominant grids using type 3 wind turbines, which is a nice implication of the two-axis anti-wind RPI regulators. We use the same anti-wind RPI regulators. Of course, we have to devise some feed-forward control loops in order to achieve the grid forming capability of the type 3 wind turbine. Again, we consider the primary energy resource, and which is nice. And this work was led by my student, Hugo and Dan. Here another positive implication is about the positive sequence simulation of grid forming technology. So some of the advances we made here is a modeling the center of inertia. For example, imagine that you have a power system that only has grid forming inverters, and the problem comes how to define the center of inertia of that system. Typically, when we have only machines, we define the center of inertia as some sort of weight average of the inertia of those machines. But we also tackle here the DC link stability problems. So it turns out when the grid side converter is working in grid forming mode, there could be instances when the PV array cannot provide enough power to supply the grid side, the demand of the grid side converter. At those times, the voltage of the capacitor can suddenly drop and then lead to a voltage collapse. If the DC link voltage collapses, then the grid side converter, the synthesizing voltages, AC voltages of the terminals of the grid side converter is not possible anymore. So then this leads to instability problems actually in the grid. So what we also invented here is a protection device to prevent the ceiling voltage collapse. So what we do now is, again, in cases when the grid side converter is transferring more power than the PV array can provide, then at that time, it kicks this protective device to prevent the ceiling voltage collapse. And in order to do that, we have to invent or to come up with a maximum power point calculation using only the measurements that are available to the terminal of the PV array. For example, the IPV, which is the current, and the VTC, which is the DC voltage of the terminal of the array. We also had to prove here some stability. So, and the challenging part was to prove first the concavity actually of the PV array model, and then do some typical Lyapunov stability theory applied to the DC link side. So all this work exists. I have here claims that nobody has considered the primary energy resource in grid forming technology, but we have actually. All right, so next of the challenges are about the fall-induced delay voltage recovery capability of hybrid PV power plants. So here the challenges now is how to coordinate the PV array with the battery energy storage, for example, using a back-post converter. And then we have the same story, right? We have a grid side converter that is interfacing the grid. It has a LC filter and it has a step-up transformer. But now here is how we coordinate these two primary energy resources, the PV array and the battery, right? And the logical part is that when we have enough solar power, we use that solar power more solar power than the solar inverter is transferring to the grid, use that solar power to transfer into the battery. And we have less solar power than the power that the solar inverter is transferring to the grid, then use the battery, right, to transfer that power. That is relatively simple. There is not much multi-objective optimization to do here. All right, so another implication here of this work actually has been the development of a new course here at Iowa State. We developed a course that is named EE6Y3, which was taught on fall 2022. The feature of this course is that married electromagnetic transient simulations and power converters and grid forming controls. So here you have here you can see here a sample of the syllabus of this course. And one of the objectives of this course was to understand the basics of simulation and control of electromagnetic transients occurring in converter-based systems. And we did simulate a purely converter-based system to study, you know, the faults that we just discussed, the studies faults that are line to ground, line to line, double line to ground, three-phase to ground, and so on. So it was very exciting. And I think with this, I'm ready to conclude my presentation. I'm pleased that I have informed some of the advances that we have developed here at Iowa State in the grid forming space for wind and solar resources. We have set forth a simple and elegant technology to engineer renewable grids that are resilient to blackouts and resilient to reliable to faults, actually. And one of the problems that we are tackling now is how to decide on the sequential restoration actions. So this is a challenge that we are trying to undertake. So now we have the capability to do, we have now the controls to do grid forming or to achieve grid forming operation of wind turbines, but we don't know how to do the restoration sequence.